Today I will present a study titled Cross-Device Perception of LiDAR-Based Digital Twin Virtual Tourism. Conducted in a heritage fort environment, the focus of this presentation is to examine how different display devices, specifically a laptop, tablet, smartphone, and VR headset affect user perception in a LiDAR-based digital twin setting. I will briefly introduce the background and motivation, describe the experimental setup and measurement framework, present the main results, and conclude with design implications for digital heritage applications. LiDAR-based digital twins are increasingly used for documenting and presenting cultural heritage sites. They can capture geometric detail and surface texture with high precision, which is valuable for conservation, analysis, and interpretation at the same time. Access to digital heritage content is no longer limited to a single type of device. People use smartphones, tablets, laptops, and immersive VR systems to explore these environments. However, it is not yet clear whether these different devices support the same level of perceptual performance. For example, in terms of recognizing textures, reading embedded information, or understanding spatial layouts. This gap motivates the present study. We wanted to understand, in a controlled setting, how device characteristics might systematically influence perception in a LiDAR-based digital twin of a heritage fort. Our study is guided by a single overarching research question. How do display device characteristics influence user perception of texture detail, textual information, and spatial understanding in a LiDAR-based digital twin environment? More concretely, we focus on three aspects: the ability to recognize visual details, such as masonry textures and small architectural features, the ability to read and comprehend embedded textual information, such as interpretive signage, the sense of spatial presence, and understanding of fort's layout. These three dimensions correspond to typical goals in digital heritage: perceiving material qualities, understanding historical information, and forming a mental model of the spatial structure. To address this question, we used a LiDAR-based digital twin of a historic coastal fort as our test environment. The site was selected for several reasons. It contains a variety of architectural elements, including casemates, ramparts, gun emplacements, and circulation corridors. The masonry exhibits distinct textures and weathering patterns, which are relevant for detail recognition. The environment operates at multiple spatial scales, ranging from narrow passages to open parade grounds. We embedded interpretive text into the model, comparable to what might be present in a virtual tour. The LiDAR acquisition produced over 250 million data points, which were processed into a navigable 3D model with high geometric fidelity. This provided a stable, identical base environment across all device conditions. We compared 4 device types, each representing a typical usage context: a 17-inch laptop representing a conventional desktop-style viewing setup, an 11-inch tablet representing a medium-sized mobile display used in museum or field contexts, a 6.1-inch smartphone representing the most accessible but smallest display commonly used by the general public, a VR headset with a wide field of view and head-track navigation representing an immersive 3D experience. Participants were randomly assigned to one of these 4 device conditions. The underlying 3D content and tasks were held constant. Only the display and interaction characteristics changed. This allowed us to attribute observed differences to the device, rather than to differences in content. We evaluated user perception using a 3-dimensional measurement framework. Visual detail recognition. Participants performed tasks that required identifying surface characteristics such as masonry patterns, material transitions, and small architectural details. Performance was recorded as accuracy in recognizing and describing these details. Text information recognition. Participants were asked to read interpretive text embedded in the environment at different distances and orientations. We measured reading accuracy and comprehension to assess how well each device supported textual interpretation, spatial presence and understanding, used questionnaire items and spatial recall tasks to evaluate how strongly participants felt located within the environment and how well they understood the overall layout of the fort. We first examined visual detail recognition across the 4 devices. The results show a consistent pattern. Devices with larger physical display areas, such as laptops and tablets, tended to support higher accuracy in identifying small textures, material boundaries, and architectural details. Smartphones, due to their smaller screen size, showed lower performance on the same tasks. The VR headset also showed moderate accuracy, influenced by headset optics and resolution constraints. Overall, the data suggests that field of view, physical screen size, and display clarity collectively influence detail perception, and these properties differ across devices. For textual information, we observed pronounced variation among the 4 devices. Laptops and tablets supported the highest reading accuracy, primarily due to display size and comfortable reading distance. Smartphones required more zooming behavior and produced lower accuracy scores, reflecting the limitations of small physical screen dimensions in the VR condition. Text legibility depended on the combination of display resolution and optical characteristics, resulting in mid-range performance across all conditions. The ability to read embedded text was strongly correlated with how large the text appeared in the user's visual field, independent of the underlying model quality. This suggests that text-based interpretation is highly sensitive to display characteristics. We also examined spatial understanding, including participants' ability to form a mental model of the fort's layout and circulation structure. Performance differed across devices, reflecting differences in field of view, interaction style, and depth cues. Participants using devices with wider visual coverage, including large screens and immersive displays, tended to report clearer spatial orientation. Those using smaller displays, such as smartphones, reported more difficulty maintaining a sense of overall layout. VR, laptop, and tablet conditions showed varying strengths depending on the specific task. But the general observation is that spatial comprehension improves when users can view more of the environment at once, either through a wider field of view or a physically larger display area. Smartphones, due to their limited viewport, showed comparatively lower performance for spatial orientation tasks. By viewing all 3 perceptual dimensions together, detail recognition, text comprehension, and spatial understanding, we can derive a consolidated interpretation. Devices with larger screen areas tend to support better detail and text perception. Devices offering wider visual coverage, whether through field of view or display size, tend to support stronger spatial comprehension. Devices with small display surfaces, such as smartphones, show consistent challenges across all 3 perceptual dimensions, rather than dividing the devices into separate categories. The results reflect a continuous gradient based on display properties. This implies that perceptual performance is not device-specific per se, but strongly linked to fundamental visual factors such as image size, viewing distance, field of view, and clarity. Based on these observations, the design recommendations focus on aligning content presentation with measurable display characteristics for devices with small display areas. Reducing visual and textual density is advisable, along with alternative modalities such as audio for devices with moderate to large display areas, providing zooming capabilities, comparison views, or annotation tools can support more analytical exploration for devices offering wide fields of view. Spatial information can be communicated more effectively through layout-based cues rather than text. The main takeaway is that Digital heritage applications should be device aware, not in that sense of creating four separate versions, but by adapting to fundamental perceptual affordances. In conclusion, this study demonstrates that perceptual performance in digital twin heritage environments varies systematically across different device types, primarily due to differences in display characteristics rather than differences in content. Texture recognition, text readability, and spatial comprehension are all influenced by how much visual information the device can present at once and how clearly it can display that information. These findings highlight the importance of designing digital heritage experiences that take display constraints into account to support consistent interpretive quality. Thank you.